Okay, so we're now going to move on to the second part of the discussion about the I2C serial communication system on the LPC802. The LPC802 is found on the OM40000 board at the very center of the board, and it will be communicating with the LM75 temperature sensor that is connected between these two over I2C. The I2C system allows the SDA and SCL wires between the processor and the temperature sensor to communicate. What will be happening in the program that you're about to see is that there will be a heartbeat that will be generated and LEDs will be flashed at a specific frequency in response to the interrupt service routine that is generated by the system timer. Inside of the system timer interrupt service routine, there'll be sampling of the analog to digital converter, and there will be a message basically passed via a global variable to the wake up timer and its interrupt service routine that will allow two other LEDs to flash at a frequency that is proportional to basically a difference or proportional to the value of the temperature at the temperature sensor. Okay, so here's the code that we're using. It's based on some SDK code from the LPC802 and as well as demonstration code that was provided by NXP for the OM40000 board. Okay, we're going to be using PIO 8 and PIO 9 for the wake up timer and the system timer interrupt service routines. In here, what you have is, at the beginning of the code, we have a description of a number of defined values, some variables. I note that global variables have a G at the front, just so that you know it's a global variable. We have some defined values for the wake-up timer. And let me see, what else do we have? We've got an address for the LM75. You use addresses on the A lines or wires on the LM75 to specify whether or not you're dealing with that one or another one. In our case, the LM75 has a hard-coded value because the assumption is that there's only one I2C device on the bus. And we don't have to change that. It's set, and that is the value to which it's set. We also have a number of masks that are defined for control of the primary and secondary devices. Some more defined values over here as well. Basically, if you're interested in seeing what these codes mean with respect to receive ready, transmit ready, acknowledgements, idle conditions, they're all listed inside of table 187 of the LPC802 manual. These are conditions that are important to understand for your code in order to be able to get the right sequence of commands between the 802 processor and the LM75. Below we have a few prototypes. Of course, in a C program, you have to define the prototypes of functions before they're encountered. Sometimes you put them in a header file. Otherwise, if you're just writing everything in one C file, you put them at the beginning of the C main file that you're dealing with. And so we have functions here related to initializing the LM75, reading the LM75, and establishing things like the frequency or baud rate of the LPC802's connection to the LM75. We have some more global variables over here. And yeah, here we go. So we're going to start by defining the interrupt service routine for the system timer. Basically what's going on is that the system timer has an interrupt service routine that increments a particular global variable so we can keep track of time. And what we're seeing is that every time the system timer runs, it checks to see if it is run basically more or equal to 5 times. So we want to see that the ISR has run basically 5 times. At which point it reads the temperature, because you don't need to read the analog to digital converter temperature value very often. And so every 5th time through the system timer, it reads the temperature via the LM75. And then basically what will happen from there is that you end up toggling the LED that's associated with the system timer so that you can see the heartbeat. Okay, so this is the heartbeat right here. Next. Based on the temperature value, what we want to do is modify the frequency of the wake up timer. And the way we do that is just basically a bunch of if and else if statements. And we're looking to see, is the temperature value number that's generated by the LM75 less than or equal to 20, between 20 and 22, between 22 and 24, between 24 and 26, between 26 and 28, or if it's above 29. So basically we're looking at values that are bracketed by basically 20, there we go, to 29. There we go, 20 to 29. And so basically what ends up happening is that we modify the global variable. Now this is being written inside of the system timer ISR. The global variable for the wake up timer reload value, it's going to use the baseline value and multiply it by 20. If it's 20 or under that temperature value. If it's between 20 and 22, then basically it'll take the baseline value, multiply it by 10 and load it into the other interrupt service routine update for the wake up timer. And then so on and so forth. Basically, it's going to get smaller and smaller values of this value until we get to a really small value over here if the temperature reading is above 29. Okay, so the greatest values are if the temperature value is 20 or below. The smallest ones will be if it's if it's 29 or above, which means basically we're going to be reloading smaller numbers here, large numbers there, which means the effect will be that we will have a slower, slower, it's not writing very well, slower value of the wake up timer, or less frequent value of the wake up timer for values under 20, and more frequent if it's above 29. Okay, next thing to point out is that we are going to use the switch matrix to connect the pins on the outside of the chip to the I2C system, and so we're going to be connecting up GPIO the LPC802. So we use the switch matrix to do that. Okay. So here's some of the code during the initialization phase of the LM75. Basically remember that for just about any peripheral that we have on the LPC802, you need to turn on the switch matrix using the clock control for the AHB bus. After that, we have to, as we saw in the table just before, we have to look at the switch matrix, and we have to look inside of the pin assignment 5 register. Okay, and in that case we have to basically do an examination. Well, we have to basically set up the SCL and SDA lines, and we're going to be popping in value 16 into SCL. We're going to be popping in value 10 into SDA because it's GPIO or PIO 16 that goes to SCL and PIO 10 that goes into the SDA. From there we turn off the switch matrix. Okay, after that, oh right, so we are now using the clock control to turn on the I2C system, and then we are resetting the I2C system. So we've turned on the switch matrix, assigned the pins, then we turn on the I2C, and we reset the I2C just like we would do for some of the other peripheral modules on the LPC802. From here, we have to choose the source of the clocking, the timing clock of the I2C system, and so we're going to be using the FRO as the source of clock, which makes sense because that's used for just about everything on the LPC802. All right, from there, we are basically setting up the primary system being the LPC802. And then we are going to set the baud rate, or the frequency, not the FRO frequency, but the frequency of the clocking signal that comes out of the I2C. Okay. Back in the day, if you had a modem to connect up to the internet, you would get different speeds of modem, 56K or 9600 baud and things like that. Here we're doing basically the same thing, but it's with the I2C system. Now, it's relatively complicated to set up, and so there is a dedicated function that's provided by NXP to make that baud rate set. Okay, and I'll show you how that's done. But basically, we're assuming that we have a 12 megahertz FRO, and we are wanting to run the I2C system at 100 kilohertz, or 100,000 hertz. Okay, we'll talk about that baud rate setting later on. The next thing that's important to point out is that we have an LM75 read function, and reading the LM75 is actually relatively complicated. It happens in multiple stages that we saw earlier. Here is the code as outlined in the first part video. So basically what you have here is one message. Then we have another message that's sent, and then we have a third message that's sent. In the first message, we're sending an address with a 0 appended to it. Then we send the pointer zeros, and then after that, we're sending the address again and appending a 1 to the end of that packet of information. So 1, 2, 3 messages sent from the LPC802 to the LM75, and of course there is an acknowledgement that's waited for by the LPC802 from the LM75, because we have to have this sort of back and forth negotiation that's going on. Okay, so there's basically these waiting functions right here that are called in order to make sure that the I2C system is ready for the next transmission. Here's some more waiting, and what you see at the end is that, so that's the waiting right there. What we then do after we've waited, and it doesn't have to be a very long period of time, there will be information received from the LM75 that will be sent into the 802, and it will be stored automatically by the 802 inside of a register called MST DAT for data. Okay, and so once it receives that, it knows that it has to wait a little bit more. It will spin or wait. Okay, so it's just going to wait some more, and then we have another. Basically, it's a second packet of information from the LM75, and you have the first, sort of the 0th cell in the array and the first cell in the array, or cell 1 and cell 0. Okay, what you end up having is data stored in cell 0, and then you have data stored in cell 1, and those two values will be connected or brought together shortly in order to make one numeric value. And the reason is because you only have 8 bits in each one of these transmissions, and we have a total of 11 bits coming from the ADC that's on board the LM75. Okay, so now that we have the 2 buffers that are full, what you end up doing is converting those 2 values into a single value that's stored in data. And we do that by doing some bit shifting and bit shifting of the cell 0 and cell 1, and then multiplying it by a certain factor right there. And that gives you a particular value that represents the temperature on board the LM75. So that was another function. Next, we have the main function. Okay, and the main function basically requires that you start by disabling interrupts. You do the clock selection. This is basically to get your FRO started, right? So we've been doing that a few times. In our case, we're making sure that the FRO is the 12 megahertz FRO as opposed to 9 or 15. From there, we need to set up GPIO, right? Because we have to have LEDs that flash on and off. So here's the GPIO setup, and then we end up having the LEDs 1 and 2 turned on. Clock config. In this case, we are going to, this is for the system tick. Okay, so this is when we're setting up the interrupt service routine for the system timer. All right. After that, we initialize the LM75. Then we initialize the wake up timer. Now everything's set up, so we have wake up timer, we have system timer, we have LM75 and the I2C. Now we can re-enable interrupts, and then we drop into an infinite loop that does basically nothing inside except for calling the no operation assembler command. All right, some other functions that have been called in here that are important to point out. So we have a wait function. So when the I2C system is running, in a number of cases, it's important for the I2C module to wait for the reception, or to wait until it's possible to receive something, or to have cleared out a register that's inside of the I2C module. So we have a wait system inside of the I2C module. And basically what we're doing is we're checking internally in the status register. We're making sure that the pending condition is dealt with. Okay, so as long as we're waiting or pending an operation, it will loop over and over. Okay, basically it's an infinite loop right here. Well, it's an infinite loop until the pending bit changes. If for whatever reason we get stuck, there is a way of setting this up so that basically if you get stuck and you want to signal the fact that you got stuck, the LED basically will be made, LED number 2 right here will be made to remain on, not flash anymore, but turn on continuously, because then it goes into another infinite loop right here. So this is a really straightforward way of debugging. Okay, if your system is hung up waiting for I2C. All right, so that was for defining wait conditions to make sure that the I2C module was ready to process information. The next thing that's important to talk about is the setting of the frequency at which information is sent or received by the I2C module, or setting the baud rate. And basically what you end up having is code that I took from the demonstration code for the LPC802. It's a relatively complicated function, but basically it's taking a look at what the source clock is, the desired baud rate, and it's coming up with, and we've talked about these prescalers. It's basically setting up a scaling value to make sure that you're as close as you can to the desired baud rate as possible. It's actually relatively common to have baud rates that are a little bit off from the desired value. It happens relatively frequently. It's actually in general really hard to get exactly the frequency that you want based on the internal clocks that are available to these modules, the I2C or SPI or UART modules. So there's often a little bit of an error condition or an error value between what is desired and was actually implemented. And so this algorithm right here makes it possible to hunt for basically a divider or prescaling system or value that gets you as close as you can get to the baud rate that you desire, that was set in the function when it's called. Okay, and so what you end up having here is the assignment of the clock divider value. Okay, clock divider is right here, and then you assign the timing configuration, and there's two macros which are like functions a little bit. They're defined inside of LPC802, and those are called here and there to ensure that the timing configuration is between two particular conditions. All right, from there what we have is a wake up timer configuration that's done. You can see the wake up timer is turned on. You disable the interrupt service routines or requests for the wake up timer. Then we have to turn it on using the low power oscillator. Okay, we're going to run the 1 megahertz low power oscillator into the wake up timer. We're going to enable that, and we reset the wake up timer, right? We're resetting. And then we load it with the reload value into the count register. Once that's done, the wake up timer is ready to go, and it's actually going. And we get the wake up timer's interrupt service routine or interrupt request turned back on via NVIC. All right, we're almost done. Then we have the wake up timer interrupt request handler. And basically what's happening here is you have to reset every time you call the interrupt service routine. You have to reset the alarm flag that was generated to make it actually get called. And then you load a new value into the wake up timer count register. Do you remember where this came from? It came from SysTick. And that SysTick routine, the SysTick ISR, called or set the global variable for wake up timer reload via the values that were from the I2C temperature sensor. And that, ladies and gentlemen, is that. So there you go, 2 parts for the I2C system on the LPC802. Good luck with getting it programmed.